Hi guys, this is SkyVault, and welcome to this random video that I'm putting up. So what I'm showing off to you today is just a fun little project I've been working on in my spare time. What I'm making is a scripting language. It's a scripting language that I'm naming Vault. That's a working name. I have a couple other names that I'm thinking about, but yeah, for now it's called VaultLang, Vault Script, whatever you want to call it. And yeah, so first off, this scripting language is not a competitor for anything. This is just a language for me to learn, for me to experiment with some of the ideas that I've had, and potentially use inside my game engines and stuff, kind of like you would like Lua, but I would use it more for like loading data, making it so that you can evaluate certain aspects of it, so you can generate, the data, stuff like that. Just small little. It's just a really small little scripting language for games. That's my goal. Yeah, so let me just run it real quick. This video, I want to do kind of like a more deep dive, showing off the systems a little bit, how it works. So if that's your jam, then yeah, feel free to stay tuned. If not, just stay while I show you some of the features of Vault. So first off, we are at version 0. I'm not even going to make this a minor version because this is way early in development. But even though it's early in development, you can still do things like evaluate 1 plus 2 plus 3. You can do things like if, 10 is greater than 2, then print hello world, stuff like that, And then it's going to print hello world. It prints it twice. The only reason why it does that is because if statements are expressions, so the last value that gets evaluated in the body will get returned from the if statement or if expression. And print line will basically convert whatever it's taking in to a string. It will print that to standard out and then also return that string. So if I just did print line 1, 2, 3, hello world, then you can see, okay, so it's not going to find this. That's a bug. This should work, but it's going to print 1, 2, 3, hello, and then something I call unit. So one thing you'll notice if you're familiar with a lot of different types of scripting languages, it has kind of an unusual syntax. You'll see that here everything's surrounded in parentheses. So this type of language here. Let me give you more of an example of what this language is. This language is a Lisp-like, a scheme-like programming language. I followed a lot of inspiration from like Chicken Scheme and all that. I do have another programming language that is not a Lisp-like one, but right now, because the syntax for a Lisp is super simple, you're essentially writing the abstract syntax tree for code, Because the syntax is so simple, I don't have to worry about syntax, I don't have to worry about parsing as much. I just have to worry about the actual runtime, which is the thing that I'm really interested in. In the future, if this runtime becomes stable and cool enough, then I'll port it over to my other programming language, which does have a really nice, clean, kind of OCaml, not OCaml, I would say more like F#-esque, syntax. But for right now, I'm just trying to make this one programming language work really well and really fast. As you can see, I have bindings, really not complete bindings, but some bindings for raylib. Before I show off the bindings for raylib, I kind of want to show how this language works. So let me just delete all this code right here. First off, let's try writing a factorial function. So if you don't know what a factorial function is, basically what it is it takes, let's say we want to find the factorial of 5. Well, the way that works, to do that, you'll just multiply 5 by 4, by 3, by 2, by 1. So basically it just, multiplies all the numbers underneath it all the way up, and that will be the factorial, which that should be, I believe, 120 or 140 or something, or 240. I don't know. We'll find out. So the way to define a function is you use the keyword defun, right? And then we're going to give it the function name. So we're going to name it fact. And then this inside parentheses, we're going to pass in, or we're going to say what kind of arguments it takes in. It's going to take in an n. And then we're going to check if n is less than 2. If it is less than 2, then we're just going to return 1. Otherwise, we're going to return n times fact of n minus 1. So this demonstrates that my programming language does have recursion. It isn't tail call optimized, so you can Stack Overflow. And right now there isn't a good warning for a Stack Overflow. You basically just run out of memory. In the future, of course, I'll be implementing that. So let's try the factorial of 5 and see what that is equal to. Factorial, by the way, is also in math described with a exclamation mark. So exclamation mark and then the number 5. That means the factorial of 5. All right. Anyway, so let's run this. Actually, this is going to run the REPL read eval print loop. So let's just change my config here to run our script. Cool. So yeah, like I said, the factorial of 5 is 120 right there. So we can see that it works. And I might do a video later on Lisps and how Lisps and schemes, the programming language style Lisp, how those actually work behind the scenes. Maybe some syntactically I can show off some of the cool things that you can do with it. For right now, I'm not going to go into too much detail, but yeah, I can just show you that you can write code here. Yeah, it does a lot of stuff. So let's go into some of the details on how this language actually works. So I actually took a lot of inspiration from the Lua source code. Of course, Lua is written in C++ or C, whereas my scripting language is written in C++. Originally, I was going to write it in C, but C++ gives us a lot of really awesome tools to help generate native functions and stuff like that I can run within my own scripting language. So because of that, I decided to go with C++. So yeah, some of the inspiration shows up with how objects are represented. So an object is like either a number or a boolean or even a table or a list. Basically every value, everything is basically a object. Even the source code itself gets compiled and translated into a object, basically a list, right? And I'll go into more detail about that maybe in the video covering schemes and Lisps. But for right now, yeah, all the objects are basically everything is an object. And the way I represent that is basically using a tagged union. So I have, a value, a vault value, which is basically a union of all the possible values. And if you don't know what a union is, it basically, every single one of these will share its own, it will share a location in memory. So this value will only be as big as the largest value, which would probably be string. In the future, it's going to be the dictionary. I don't actually have dictionary implemented. It's just implemented as a key value pair list. So the environment is really slow to actually find symbols and stuff in, but I'll worry about that in the future. Okay, so yeah, you have this union value, and then we have an object. The object has the union value, and then it also has a value type. So this is how we know which type this object is, whether it's a string, a number, a native C function, whatever. Right now, my programming language is just purely reference counted. So in the future, I have a plan to implement a very simple garbage collector, probably. I thought I could get away with just reference counting everything, but right now I'm leaking a ton of memory. I'm actually to a point where I want to actually start using this language, so I should probably start managing memory a little bit smarter. So yeah, right now everything's just reference counted. When the reference goes to 0, it'll get freed. And yeah, these are just some methods on every single object to, I actually need to get rid of this. This is how you index an object, so you can index a list. Lists are represented as not key value pairs, as basically a linked list. A lot like most Lisps out there. So yeah, you have your slot, which is the value, and then the next value in the list. So yeah, we have the different data types that I support are all listed here. We also support pairs. I just don't have it in the code really because a pair is just a list. But yeah, we have booleans. And also dictionaries aren't supported. There are 3 different function types which are going to be unified into 2. So you have a function, which is just a regular vault script function, which you can define in your own code. Then you have a C function. Now what this is basically a lambda, and it receives the environment and then a list of arguments. And the very last one, I might keep this one because it might be useful to toy around in like very advanced code, toy around with the environment a bit. So you might want to have access to that. So I might keep it around. But the very last one I'm pretty excited about, I just implemented. It's called a function bridge. And it's basically a bridge between native C functions and the functions that we write in Vault. And there's a lot of code down here that actually converts to and fro from a Vault object to a regular C++ object. And then this is a bridge wrapper. I didn't write all this code myself. I had a lot of help with it because I'm not a template guru at all. But this supports like just about any C function besides C functions that have like object parameters, so like structure parameters and stuff like that. I don't quite support that. I still need to think about how I want to do that. But yeah, so you can basically let me show this off. I have a file here called Prelude. If you know how Lisps work, or a lot of scripting languages work, essentially most of the code to make all these run, like define right here, this is a function, right? The code that defines functions is in itself a function. If is a function. It's a function that takes in a expression, it takes in a consequent, and then a alternative, I believe. So this is it'll basically run this code if this expression is true. Otherwise, it'll run this code. So it's considered a special form, but it is still a function, and that function is actually defined in here. So these are all the functions that are available. You got equals, greater than, less than or equal to, and I can kind of show a lot of these off too if I run the. Let me run the REPL, the read eval print loop. Okay, so yeah, if I run the code right now, we can see the REPL right here. So I mean, we can try minus. Let's try subtraction. Let's do 3 minus 2.1. We get 0.9, which I believe is to be expected, right? The cool thing about this syntax also is you can do things like this, right? You can like most languages, programming languages have infix notation. So like if I want to express what I just wrote up there in like Python or something, then I would have to spread the star operator across all of the arguments. Let me see if I can make this a little bigger. Maybe I can. Maybe not while the code. Oh, here we go. So you would have to put a symbol the star symbol in between all of the numbers. But because actually that shouldn't evaluate, but whatever. Some bugs. But because the star symbol is a function, right? It's a function, and these are the arguments of the function. We can just call it without putting it in between. We can call times with 1, 2, 3, 4, 5, 6. We can also, there's multiplication. There's, we can get pi. Actually it's a function, so you'd call it. We got things like define, so we can define variables. So I can say define x to be the string hello, and then we can evaluate x. We can also print x and then world like this, and it's gonna say hello world. We can also set values, so x isn't immutable, so I can set it to like the new value 100, and there's no type safety, so x can be anything, right? So you can set it to hello, you can set it to a boolean, you can later set it to a float, whatever you want. That might change in the future as I experiment with the different features that I want to add to this language. Do blocks and paragons, you can think of these as, they're kind of like in other programming languages where you can have curly braces, but the difference between what they do is that they actually evaluate every single expression in the list and then returns the last value in the list. So, this is going to return 3. So I can say do print line hello, add 1 and 2, and then just return 32. And it's going to print hello, and then this happens, but the result gets thrown away, and then it returns 32. You can convert from a number to an int str, and what's nice about this syntax also is that your names can be very expressive. So I can have a variable that looks like, int to float, something like that if I wanted to int to float function or value. Or I can make, like traditionally in Lisps, constant values are, delimited, or global values are surrounded by what they call like earmuffs, which are, just stars. So, I can create a variable called pi, which is just stars and then the letter pi, or the word pi. And yeah, you can see that it evaluates fine. So you can have some pretty crazy names. Oh, another thing I want to mention is that we actually do have a very primitive form of quoting. So if you don't know what quoting is, it's a pretty advanced. It's basically the bread and butter of Lisps, and the reason why they're so cool and fun to work with, and the reason why I made this a Lisp, because it would be very useful for games. But yeah, so quoting basically says don't evaluate this list. Normally what happens, if I just write 1, 2, 3, or 2, let's go back. 1, 2, 3, we're going to have an error. Can't evaluate function 1. Because in this language, anything that is surrounded in quotes, or sorry, parentheses, is a function. So, basically this is a function call, right? It's a function call. This is calling the function plus with the arguments 1, 2, and 3. So if we don't want that function to evaluate, if we want it to instead just return the list with the symbol plus and the symbol 1, 2, and 3, then we will quote it like that. We don't have unquote though, so once we have unquote, we should be able. I should be able to do full, the whole macro thing, and then maybe I'll implement quasi-quoting and all that crazy stuff. But that's just for the future. I'm still not 100% sure how to do quoting. For instance, it's not actually. I don't believe it's recursive, or yeah, recursive. So let's give that a shot. Okay, so never mind. I stand corrected. It is recursive. So yeah, let's just keep going through. Yeah, we have while loop, we have read and print. Everything that you would expect. Car, cons, cutter. I'm going to change these names to first and rest, probably, like traditionally. You have let bindings. I'll go into more depth about how all this works later. But anyway, so the environment is basically where all the variables are stored. And how it's represented is essentially a linked list of pairs. So it's a two-dimensional linked list. And scopes work by putting a, consing. I don't know if you know what consing, it basically means putting another element at the front of the list. We basically put another pair on the front of the list. I'm having a hard time explaining myself. I might go into more detail. But basically, you can think of the environment as a dictionary where you can put in key value pairs. So I'm basically saying that the atom let is equal to a new C function, and then I can pass in the lambda. Anyway, I got way sidetracked. I wanted to show off how raylib is actually being binded. And actually, let me go back here and let's see if I can undo, and we can check out the raylib example. Here we go. So let me make sure that we're launching. Okay, we're gonna launch it. So this is just a really simple raylib example. It's not 100% working, like you can see here, X and Y. These should be 100 and 200, and the square should be there. But I might have some issues there with how scopes work and stuff. But yeah, you can see that we're drawing a red rectangle, and we have an FPS. Right now, my programming language is atrociously slow, so it's going to be really slow right here. But yeah. Anyway, yeah, we got a window. And the way I bind these C functions, right, is just by calling new native and then passing in the function. And it will automatically figure out how to convert to and fro from vault objects to regular C values. So, init window takes in an int and 2 ints and then a const char star. And we just automatically know how to convert back and forth. And it will essentially just create a new function that we can just call. Before, the way I had to do it is we would have to, if we look in here, we would have to write functions like this where we would have to get the arguments, which is a linked list, right? And then we'd have to shift out all the values that we want and then pass those into the function manually. But now, yeah, we can just implement, cosine and sine and atan just by, using the native C functions. And it just works, which is pretty cool. I guess I can go into just how the reader or how everything is kind of set up. So when I read a script file, essentially I just read there's something called read code. Okay, so read file will just read the entire contents of the file into a string. In the future, we might actually stream that in, but for right now, yeah, we just read the entire file. And then in here in read code, we basically create an iterator, or we take the iterator, the starting iterator and the end iterator, and then we will read a progon. And this is a recursive descent, I guess, style parser. Very simple. Of course, a Lisp is incredibly simple. There's not that much syntax. So, we will keep reading expressions and then pack that into a progon, which is just, remember, just a list of expressions. And then, yeah, expression, it will read a token. So you can think of it, so a token is basically a word or something. So in this code, requires a token. Open parentheses a token. This string is a token. So basically, read token will bump the iterator and return you basically that token. And then we can switch on the type. I can actually go into the read token if you're curious of how it works. It's just, it checks if it's at the end, it skips all the white space, and then, it handles all the symbols. This is how it parses numbers. Really simple. We don't do any checks to see if there's more precision than we handle yet. Again, I'm just trying to get this thing working, and then I'll be working on really smoothing it out. But yeah, that's basically how it works. Just single character expression tokens just get returned like that. Yeah, we switch on the token type, and then we return a new value. So if it's a number literal, then we'll return a new number. If it's an atom, which you can think of an atom like a word, like if or expr or a variable name, that's an atom. Boolean strings, If we see an open parenthesis, then we'll create a new list because open parentheses that represents a list, right? And then we'll continue just read all the expressions within that list. Once we hit a unit, you can think of unit as kind of like null. Once we hit null, the end of the list, we just return that list. Otherwise, we just push that the item onto the list. You can see push is just, this is how push is defined. Again, it's just a linked list implementation. Yeah, so that's how, that's reading expressions. Once we read the expression into an object, then we will, let me go back to main, into the object, then we'll actually evaluate the object. Right now, there's no intermediate representation of our programming language. It's just the abstract syntax tree, which is just, the list of tokens and, everything. So yeah, when we evaluate, we look at what the type of the object is. If it's a unit, a boolean, a number, or a string, those are what's referred to as self-evaluating, right? So a number, if I just type in, let's open up the REPL. I really need to work on my build scripts to make this a little easier, but anyway. So we just open up the REPL. If I just type in 123, 123 evaluates to itself. 123 just evaluates to itself. So we just return itself. An atom is different, right? If we type in x, x doesn't just return, right? We can quote it, and then it won't evaluate, and then we'll get an x. But x is like a variable, right? So it has to find itself in the environment. So we can set x to like 123. Oh, that shouldn't have happened. All right, let's try this again. All right, if we can't find x in, oh, okay, so yes, okay. Sorry, we're using set. Set basically sets a value that already exists. Def defines a new one. So anyway, we can define x to be 123. And then now, when we evaluate x, it's going to go in evaluate expr. This is going to be of type atom, right? It's going to switch and then find the atom type here. Then we're going to find the object, right? The object that the atom represents in the environment. And this name is not good, but I can change that later. If we can't find the object, then that's where we print we can't find it. Otherwise, we return the value. So we basically get 123. Yeah, lists. We evaluate the. So let's do. Let's create a function called add, and we're just going to add A and B. So if we call add with 1 and 2, we're going to get 3. So the way this works is there is a list internally, right? There's a list that has the add, the number 1 and the number 2 in it. So we find that list, we get the length of the list. If it's equal to 0, that means we're evaluating an empty list, and that's an error, right? It might not be an error in the future. It might just evaluate to... Yeah, right now it isn't an error. It's just a warning, I guess. But if it is longer than 1, right? If there's elements in the list, then we will evaluate the first argument. The car basically means take the first element of the list. So we'll evaluate add, which will return us a function, right? And then we will invoke that function with CDR means the rest of the list. So CDR would be these two elements right here. So so if we go into invoke, we can see that this is where we handle the 3 different types of functions. You know, if the function is a C function, then we'll just directly call that C function with the environment and the args. Otherwise, we will, if it's just a vault function, then we'll get the parameters that are attached to the function. Then we'll get the body of the function. We'll create a new scope, right? Which is just consing a new list onto the environment. And then we'll iterate over the parameters and make sure that we match all the... We basically push into the environment. So, you know, 1 gets assigned to A, 2 gets assigned to B. That's where this is happening right now. And then we'll evaluate the progon, which remember is a list of expressions that returns the last value. We'll evaluate that with the new environment. So, you know, we will call 1, 2, 1. That 1 gets inserted here, 2 gets inserted here, it adds it, and then it returns 3. That's just if that just went over your head, don't worry. Like this took me a long time to actually figure out, and you know, a lot of studying other people's code and stuff like that. But that's basically all I want to show you. We do have require, so we have very simple, you know, package support. All this does is basically reads the script and then inserts all the symbols into your environment. So it's not by any means a good way to do it, but yeah, that's how I do it for now. And in this script, we have a bunch of code for controlling like the terminal escape sequences. So you can basically print colored text. So for instance, I can do print line foreground red hello world, you know, and then let's print clear. Let's clear the color again because it's going to set everything after that to red. And then if I launch the script, we will see that you know, we get red text, the foreground of red. So yeah, I'm going to build out a really nice ANSI terminal library for Vault, which is really useful for, you know, making really easy to read interfaces and stuff like that. Just to prove that scoping does work and all that, I can remove that symbol, and now we can't find, you know, the symbols and stuff like that. All right, well, you know, that's all I really had to cover. This video is really rambly. If you gained anything from it, that's great. Let me know what you guys think in the comments below. If you want a more in-depth tutorial on how to actually make a scripting language yourself, I would love to make one. Maybe like a really maybe implement BASIC or something very simple like that in the future. I would love to do that. So just let me know if you find this interesting. If not, you know, that's fine. I'll keep working on it, and I'll probably give another update later once I have something a little more concrete. But yeah, thanks guys for watching, and I hope you had a great day. Bye.